So in section 4.4, we look at some characteristics of covalent bonds. So one of the simplest characteristics of a covalent bond is its length. And the length of a covalent bond depends upon a couple of things. In particular, it depends upon the identity of the atoms involved, and that is larger atoms tend to form longer bonds. The type of bond, whether it is a single, double, or triple bond, and single bonds are the longest, double have intermediate length, and triple are the shortest. Now, typically a bond length will be reported in angstroms, which we write or abbreviate with this little symbol here. It's a little A with a little circle at the peak of the A, and 1 angstrom is the same as 10 to the minus 10 meters. Now, the reason for choosing this particular unit to express bond lengths is because bond lengths are normally a little bit bigger or a little bit smaller than about 1 angstrom. So let's have a look at some covalent bonds, and you can see how the identity of the atom affects the length of the covalent bond. So hydrogen atoms are very small, so the bond between two hydrogen atoms is one of the smaller ones that we see or is the smallest one that we see in the table here. When we bond hydrogen to carbon, because carbon is larger than hydrogen, you can see that the bond gets longer. So if we look further down our list, here we see carbon bonded to carbon, having a bond length of about 154 times 10 to the minus 12 meters. Whereas if we bond carbon to the smaller oxygen, we can see that the bond length gets a little smaller and it drops down to 143 by 10 to the minus 12 meters. It's important to recognize that most bonds are not between identical atoms, but are rather between different types of atoms. And as a result of this, the electrons that make up the bond are not shared exactly evenly between the atoms. For example, when we share electrons between a hydrogen atom, which has 1 proton in its nucleus, and a chlorine atom, which has 17 protons in its nucleus, it's not surprising that the atoms lie a lot closer to the chlorine end of the bond than they do the hydrogen end of the bond. This type of bond, where we have uneven sharing of electrons, is described as a polar covalent bond. And we have a couple of ways of indicating that a bond is a polar covalent bond. One way is to use what we call a polar arrow. And in a polar arrow, what we do is we draw an arrow directed towards the atom that gets the greatest share of electrons, and then we make the other end of that arrow into a positive sign. Another way of indicating that we have an equal sharing of electrons is the more positive end of the bond, the end of the bond that has fewer electrons, we label as delta positive, and the more negative end of the bond, the one that has a greater share of the electrons, we label as delta minus. So either of these two ways are appropriate for indicating that a bond is a polar covalent bond. A little bit of language that you'll see people using when they're talking about polar covalent bonds is that they will say that the bond has a dipole. Di just means two, pole just means whether it is a positive or a negative pole. So a bond that has a dipole has a positive end and a negative end. So we can predict what pairs of atoms will form polar covalent bonds with unequal sharing of electrons using the periodic table. And the reason this is because the tendency of an atom to pull electrons towards itself, that it is to pull shared electrons towards itself, increases from the bottom left of the periodic table towards the top right of the periodic table. So there are a bunch of schemes that attempt to quantify the tendency of an atom to pull electrons towards itself. This tendency is called the electronegativity of an atom, often abbreviated with the letters uppercase E and N. The scale that we're going to use to express relative electronegativity is one that was developed by Linus Pauling. And Linus Pauling is a Pacific Northwest local. He comes from Oregon, and he is famous not only for this electronegativity scale, but he is the only person to win 2 Nobel Prizes in two completely different disciplines independently. So most Nobel Prizes are awarded to teams of people. Linus Pauling got 2 of them all by himself. So on Linus Pauling's scale, we see the same trend of electronegativity values. They increase from the bottom left of the periodic table towards the top right, and fluorine has the highest value with an electronegativity value of 4. And then amongst the non-metals, which are those that are involved in forming covalent bonds, we see that hydrogen has the lowest value. Okay, a few of these numbers you're going to see are identical for some elements. So we can see that phosphorus and arsenic have an identical value, and the other one that comes to mind is nitrogen and chlorine have an identical value. So some of those ones that have identical values, it wouldn't be obvious from the trend, so having actual numbers can really help. So just recapping, when atoms of different types bond to one another via covalent bonds, the electrons might not be shared evenly. For example, in hydrogen chloride, because hydrogen has a much lower electronegativity value in comparison to chlorine, this means that the electrons are sucked towards the chlorine end of the molecule. We can indicate this using either delta notation or with a polar arrow. We draw a polar arrow so that the arrow is directed towards the end of the bond where the electrons are being pulled, and then the other end of the bond is turned into a plus sign. So using Pauling's scale, we can characterize bonds according to the difference in electronegativity between the atoms involved. And what we're going to say is that if the difference between the 2 atoms bonded together is less than 0.4, then we're going to call that bond non-polar. If the difference in electronegativity between the 2 atoms being joined by a covalent bond is between 1.8 and 0.4, we're going to call that a polar covalent bond. Now, if the difference in electronegativity is greater than 1.8, we don't have uneven sharing of electrons, we have complete transfer of electrons from the less electronegative element to the more electronegative element, i.e. what we actually have is an ionic bond. So using Pauling's numbers, we can classify bonds into one of these 3 different categories. It's important to recognize that not just bonds, but entire molecules can have a polarity. So if we look at this water molecule, it has 2 polar bonds, and we can see that all of the electrons are being sucked up towards the oxygen end of the molecule. And the net result of this is that the oxygen end of the molecule is more negative and the hydrogen end of the molecule is more positive. So this whole molecule is described as being polar. So you can recognize polar molecules because they will have an unsymmetrical distribution of electrons around their central atom. And that's exactly what we're seeing here. Electrons are being sucked up towards the oxygen, leaving the hydrogen end of the molecule deficient. Because water molecules have a positive end and a negative end, they attract one another. Positives attract negatives. And you probably noticed this if you spill some water, it kind of beats to itself. It sticks together. The attraction that exists between water molecules is called a hydrogen bond. And these bonds are extremely important in biochemistry, which we'll be studying next quarter. In particular, they give rise to the DNA double helix, and they're also important in what we call protein folding, which gives rise to the characteristic shapes of our proteins and enzymes. Now, you can easily recognize whether a molecule is polar or not if you have a correct Lewis diagram. And the reason is because there will always be more than one type of thing, and by thing I mean either an atom or a lone pair, attached to the central atom. For example, we can tell that water is a polar molecule because it has lone pairs and also hydrogen atoms attached to the central atom. So because there are two things on the central atom, the distribution of electrons around the central atom is asymmetric, and we know that this is a polar molecule. Now, methane we can recognize immediately as being a non-polar molecule because attached to the central carbon atom there is only the one kind of thing, which in this case is a hydrogen atom. So methane is a non-polar molecule and it does not have a positive end and a negative end. So it's important to recognize that molecules that are polar will interact strongly with other polar molecules. For example, carbon monoxide is polar, has a positive end and a negative end, and water is also polar. And so for this reason, the positive end of water molecules will be attracted to the negative end of carbon monoxide molecules. Molecules that are non-polar will not interact as strongly with polar molecules. For example, we wouldn't expect to see a strong interaction between methane, which is non-polar, and a polar water molecule. So in this problem from the book, we're asked to describe the electronegativity difference between each pair of atoms and the resulting polarity or bond type. So we're going to need our tables of electronegativities to do this. So let's see what we've got. So carbon, we have an electronegativity of 2.5, and oxygen, we have an electronegativity of 1.5. So the difference in electronegativity is equal to 1. So 1 is greater than 0.4 and less than 1.8. So we classify this as a polar covalent bond. Now we're going to look at the difference in electronegativity between potassium and bromine. So 2.8 and 0.8, that gives a difference in electronegativity of 2. So as 2 is bigger than 1.8, we're going to say that this is an ionic bond. I should point out that delta, the Greek letter delta, equals difference. It's just a shorthand way for writing the word difference. Some people will also use this to mean the change. Okay, so our next one is, what is the bond between two nitrogen atoms? Well, this one's easy. We don't have to think too hard. The difference in electronegativity will be equal to 0. And any bond between two identical atoms is always going to be a non-polar covalent bond. Finally, we have cesium and fluorine. So cesium 0.8, fluorine is 4. So the difference in electronegativity there, 3.2. And 3.2 is definitely bigger than 1.8. So that's going to be an ionic bond. And so what we see is that when metals bond to non-metals, we're always ending up with an ionic bond. Okay, so that concludes the section on the characteristics of covalent bonds.